So welcome everyone. This is we have a talk here today by Prof. Majumdar, who is at the Tata Institute of Fundamental Research. So he did his PhD from the Indian Institute of Science, Bangalore, and thereby went to University of
in Chicago.
Yeah, in Chicago. Then he was a postdoc for some years in the in Canada, and thereafter joined the Tata Institute of Fundamental Research in 2007. So he is the person who has formed actually the cosmology group here, and he's linked with a lot of projects throughout the world, and those coming to ACT or others also. It's a lot of projects. And now the cosmology group of Tata Institute of Fundamental Research is perhaps now the largest. So he has collaborations with a lot of people in the world. So he will shed some light today on today's lecture. Let's see what he has some great things for us.
Well, thanks a lot, Subhabrata. It's a real pleasure to be here. As I was telling when I was giving a talk in Johannesburg, like just a few days back, it's indeed a real pleasure when you go to some place that you've never been before. It's very exciting, and I hope what I will say is also similarly exciting. And thanks for coming to make this possible, and precious for doing all the hard work in between. So I will try to say why the name is kind of provocative, Brave New World. What's brave, what's new in it? And so this is about probing our universe. And when I say universe, it means it can probe the cosmology, or it can probe also the structures, the physics of whatever it is, with the secondary CMB and isotropies. And for people who don't know it, I'll try to quickly say what these are. The important thing is the word new. Okay, so people who are familiar with secondary CMB and isotropies will really see why this is new, because I'm going to talk about things which people doing secondaries have not done before. It has come out in a number of publications in the last 4 or 5 years. I'm getting excited about it. In fact, it started, the first idea started when I was a PhD student. So one of my chapters in my thesis had some stuff on it, and then I went back to it like 20 years later. Most of the work, the hard work, is done by this postdoc over here, Sunyaev-Zel'dovich, who is the same postdoc now applied for jobs, really smart guy, and an undergrad student who now has just moved to Austria for his PhD. Okay, let me do this fancy thing. And let's start with a very old slide on secondaries. Okay, let's start my timer so I can. So I just moved it into a PDF file, so all the pictures are together. In the PPT, things would have come one by the other. So let's start with this picture on the left top hand side. It is a picture of the CMB sky. Okay, so people are aware the CMB sky has fluctuations. There are hot and cold spots. So if you look at the CMB sky and do not filter in any spatial scale, roughly you would see something like this, some fuzzy map of the sky like this, where some spots are hotter, some spots are colder. That's what it is. These are what are known as the primary CMB. So this isotropies of this was generated at before the last scattering surface. So last scattering surface where the electrons and protons combined and the photons were free to come to us. That's at a redshift 1000, like 300,000 years after Big Bang, or 40 billion years. And this is what we have. Now, when this photon comes to us, they gather new anisotropies along the way. And to distinguish this new anisotropies from what was already there, we call these new anisotropies as secondary CMB anisotropies. So the second map is what we'll actually see now, which is a combination of primary CMB anisotropies and secondary. And we do not really see much difference. although there are secondaries over here. Over here, what we have done is taken this map and filtered it on a scale of 4R. So you see a little bit, things have been like smoothed a bit, because it's convoluted with the filter, but we really don't see the secondaries, it always there. Once we filter by a smaller scale of 2 arguments, you can suddenly see some sources. And by the time we filter with a very small scale of like 10 seconds, which is like what instruments do these days, you see all these different sources. So these were there already. It's hidden, you couldn't see before, but the idea is that if you can filter them on spatial scales, so if you go to high angular resolution observations, which is what we're doing now, and we will be doing even more in the near future, then this is what we'll see. So, for example, Planck, if you look at the large-scale structure CMB survey Planck, it will go to an angular resolution of approximately a degree, to a little less than a degree, half a degree. Whereas this is looking at much less, let's say 10 arcs. So less than an arc minute or so, you start seeing patterns. And these can be due to number of sources. Now, before going ahead, let me also say why I said mu over here. As I said, these secondaries are due to number of sources, but in the literature till now, the secondary that people have studied almost all the time is that coming from clusters of galaxies. So the CMB background photon passes through a cluster of galaxy, it gets scattered, upscattered by the hot gas, and that will give you some spectral distortion, and those are numbers of galaxies, or the cluster will be moving, that also. So basically the source secondary is clusters of galaxies. What I'm going to talk about today is not clusters of galaxies, something different. So to put it in context, there are larger surveys and proposed after post-Planck surveys, and these are the future CMB research surveys. If you look at the goal of these future surveys, there are 3 main goals. One is the search for primordial V-mode. You have heard of it. It's sort of what I call the Holy Grail. The second Holy Grail is to look at early universe spectral distortion. So just like the secondaries change the Planckian spectrum of the CMB a little bit, the initial primary CMBs may also get their Planckian spectrum changed and have a new kind of distortion called a mu-distortion. Doesn't matter. Just a distortion of the spectrum. And that distortion carries a wealth of information about early universe. What kind of physics was going on in the early universe? Whether the large relic particles were decaying, was the recombination different? All this physics was in this. That's one of the holy grail. And then the third holy grail is to look for secondary CMB, because as you can see, the primary CMB only tells you about the universe from 0 to 300,000 years. And the rest, 14 billion years, is covered by secondary CMB. So although our cosmology from CMB has been dominated by primary, now we're in the regime is going to be dominated by secondary CMB. That's what we'll talk about.
Just a quick question. Does it, so what you're saying, the secondaries, so can you measure the redshift or the time slicing?
You can measure the redshift of the time slices if you cross-correlate with a large-scale survey. So if you know what the survey is, you cross-correlate, then you can do tomography.
Is a kind of match filtering.
Not match filtering is kind of match filtering is to look at the sources, but if you can cross-correlate, let's say I know that doctors are doing this, so I have a cluster survey, I can cross-correlate with cluster surveys, and then I can basically do tomography. So people are familiar with this primary CMB pause spectrum. This is the pause spectrum of primary CMB. This is basically the correlation of the two-point correlation of anisotropies linked to the angle difference. The L is basically the inverse of the angle. So large angular differences and smaller. This is like small angular scales. And people have seen this wavy nature. This is basically the acoustic oscillations with the primary CMB. And people must be familiar with this because this is what and this is what primary CMB does. The precision cosmology that we are so proud of these days comes from this. However, this, along with that, people also do secondary CMEs, and those are these power spectra. These are from the sources. And what people have done till now is only confined mainly to this. This is the secondary CME power spectrum from galaxy clusters known as thermal Sunyaev-Zel'dovich effect. So basically, from the hot gas in the galaxy cluster random collision, the ions in the hot gas plasma is in random motion. So it's Zel'dovich effect. And then the galaxy clusters itself can move. So this bulk gas is moving, the hot gas is moving. That can give a Doppler shift to the CMB as a kinematic Sunyaev-Zel'dovich. So this is what is there till now. This is, there is the word act, which Kavi is involved with. Okay, so people do these things, and a lot of papers here in the last 10 years. And of course, we're going to the next generation of the things where we have the SPT, the SPT4, the SPT5G, the ACT, the silent serif, things like that. All there's a plethora of new surveys that is doing that. However, this space is not empty. This is something that most people do not realize. There are tons of objects in this universe, and if you look at them, if you know how to do it, you can fill up the space. And that's where the Brave New World comes in. And in the next 10 years or so, we will be able to get it. So remember, there was a primary that people looked at, there was the two secondaries, but now we have anisotropies coming from reionization, winds coming out of big galaxies, galactic winds, radio galaxies. Talk today, the really non-thermal plasma around this, quasars doing funny things, look at Anna's bubbles. So this is what we are looking at. This is an amazing picture that we are looking at the next 10 years that we can do right now, which was not possible. So the last 20 years of CME studies, this is what we're doing. It's really a great thing. Okay. So with that, let me talk about one of the sources, which is radio galaxies and non-thermal LC. This is very, very new. This is the first time someone has actually calculated how to look at CME anisotropies from non-thermal sources. So in general, when people talk about secondary CME anisotropies, the gas which scatters the electron is a thermal gas. So the anisotropies are basically due to gases in thermal motion. The anisotropies are due to the thermal motion of the gas. So basically, you know what's the energy of the gas, and can calculate this. There can be regions in the universe where the gas or whatever the electrons are non-thermal. Non-thermal means it has a far law in energy, non-thermal distribution of electrons. And those give rise to new kind of anisotropies with very, very distinct signatures. And one of the regions where we can get non-thermal, and I said this is the first step someone is doing non-thermal. We tried to look at it before, they could do it. Now we think we can. Is very galaxies. Let me come to. So here is a picture of a radio galaxy. Okay. One of them. There can be other pictures of radio galaxies. A nice picture. We have the central engine over here. From here, the jets goes in two directions. And if you look at this is a phase on radio galaxy, very nice. May not be phase on, right? And if you look at these two sides, there you can see there's two hot spots over here. This is where the jets go and hit the medium. So that's basically flows in synchrotron, radio. Also, you can see some diffuse region over here, which is also flows in radio. It will also go in X-rays as well. So now we want to look at the CME distortion. We need to sort of do a simple modeling of this. Of course, it's simple, you can make it as complicated as you want. I'm going to give you a simple model over here, and there's a long history of it. So I've taken the same picture, and I've drawn a cartoon of the radio galaxy. Few things I want to sort of emphasize. So there is the central engine. This is where the black hole is. This is what's emitting the jets. Okay. The two hotspots on two sides are at a distance. They call XA, XH over here, horizontal distance. Later I will actually write it as LJ, the length scale. And there's also a distance perpendicular to it. So it's like an ellipsoid. Both the sides grow time. And in between, there is this boom of the lobe of the radio galaxy, which is filled with non-thermal plasma. Now, where does this non-thermal plasma come from? Non-thermal plasma comes from this jet heading over here and splashing back. So think of yourself, if I'm a radio galaxy, think of yourself like I'm a person with a hose of water, and I'm on roller skates. So I turn on the water goes and hits the wall. And when it hits the wall, in this case, it is the medium, the ambient medium. It plows material, so that becomes like a wall. It flows back. Okay. But since I'm on roller skates, my distance also increases. So not only this region is filled with this bounding water, in this case, it's this rebounding non-thermal plasma, but the size also increases.
Where is the galactic plane?
Where is the
galactic plane? Are the jets going through?
Galactic plane. It's the galaxy somewhere over there.
Yeah. So the central engine is a black hole, but then you have the galactic plane.
This galaxy doesn't.
So no, I'm saying it. Is it plowing through the galaxy?
Yeah, it is plowing. So it comes out of the galaxy. So a galaxy, for example, let's say these black holes, or radio galaxies typically are in elliptical galaxies. And if I look at the optical region of elliptical galaxies, this will be somewhere.
Okay, so it's beyond the galaxy.
Yeah, the jets are so powerful that it tears out of the galaxy, goes out. But as it goes out, see, think of it, it sort of pushes material. So there's all material, intergalactic material here. It pushes material, and then that material basically gives it a motion. So this region inside is sort of discontinued from the region outside by a contact discontinuity. But there are jump conditions. That's not good. The whole idea is that here is an ellipsoidal region, which is really large enough and is growing, and then depends on the 3D guys. Now,
so determines that particular ellipsoidal region, because I can see that you're sort of using those hotspots as your foci, but then on the other side, what is restricting that as opposed to making it sphere?
Okay. So I'll come to that. So basically, the hotspot is the, sort of the maximum extent that the jet goes. Right. Beyond it, it doesn't go. So as I said, when the jet flows through the intergalactic medium, it has materials. So it sort of sweeps up this material. At some point of time, the accumulated material is swept in a very thin shell, stops the jet from moving forward. So that's like the artificial wall that is there, where it's in. Now, how much it will go will depend on with what energies things are going out. So what really tells you about this is basically what is the power of the central black hole and how long it's active. Turns out the power of the central black hole can be variable, and different. Some Q are equations for the Q, and the time will be some time scales, a billion years, 10 billion years. Now, we know that the black holes, quasars, radio galaxies, quasars, or whatever, these central black holes do not act all the time. It switches on, billion years, 10 billion years, switches off, again switches on. And the idea is very simple. These black holes are fed by the local materials sweeping inside. So it goes in, then there's a luminosity that comes out. But as it sort of collects all the materials, there is a dearth of material around it. So there is basically, because it's hungry, but it doesn't have food, so it switches off. Gravity brings in more material, again, at some point of time, switches. So this is a non-thermal plasma. The important thing is to, because this is not, there's no time to thermalize, this plasma is non-thermal. So if you look at semi-distortions, you have to calculate it different, not Sunyaev-Zel'dovich, what we did. So I'll quickly go through some equations. Equations are not really that important. It is a long history. The models can be made more complex, but I'll just give what is the flavor of the model. So assume that the radio galaxy have luminosity, central luminosity Q, take out Q, which as I said is important, and it injects little particles of some lifetime, which is T. This can be 10 million years, a million years, doesn't matter. This number is uncertain. This is uncertain, this is uncertain, so we need to know how to get this. Then the lobe expands in a surrounding gas. Gas does not have to be uniform. The gas can have a density structure. There is non-thermal electrons, so this is important because in non-thermal, the number density electrons has a power distribution of energy. So gamma is the valence factor. Then energy like this. Higher valence factor is less, lower more. And then the evolution of this radio lobes is basically given by actually very simple equation. You can make this equation more complex, but it's basically this equation. Basically an energy balance equation of the lobe. So you have energy which is going out, and some energy is lost by the work that is done, and some energy is lost by cooling. So cooling and work balances the energy that's going, and that gives you state. This also comes just from pressure balance, because it is the excess of pressure between inside the cocoon and outside the cocoon that pushes the cocoon, and that gives a pressure balance. It turns out this side, the longitudinal cocoon expands at some rate, the horizontal transversal expands at some other rate. One can do more complicated equations, as I said, what I did during my PhD. But given enough time, these two rates saturate, and observationally we see that the size, longitudinal size, the horizontal size is always like 2. Very interesting. And mathematically, one can show that it's also like 2 per time. And after that happens, the cocoon grows self-similarly. So it's always maintains ratio. That's very important. Self-similar. Okay. Now, in the medium, there's magnetic fields, so there's magnetic energy. And because there is electrons, there is a kinetic energy density. And I can write down the energy densities of magnetic field and the kinetic of the electrons in such a way that these two are with some ratio. And when equipartition happens, and this happens when the power law is this classic Fermi power law of R to the power minus 3, like energy to the power minus 3, these two are in equipartition. That's all. Okay. So those things will basically lead to energy losses. Once we have this, the radio flux that is coming out of the lobe, and remember, radio flux is coming out of the entire lobe, not just the central galaxy. That will depend on the amount of magnetic field that is there, the amount of electrons that is there, the numbers of electrons that is all synchronous. So you can calculate that. And what happens is that the electron sort of basically emits at the lambda. One thing that should be kept in mind, and it's very important, is that although the central galaxy or splashback sort of starts with some value of the non-thermal plasma, some power law, because these electrons are losing energy, and different energy electrons are losing energies at different rates. So this power law feature completely changes. So if it starts with some flatter one, it goes. So there is a change in the index of the power law. So you start with some power law of the initial spectrum of energies, it becomes a different spectrum of energies, and that depends on basically how much work is done, how much energy is lost in synchrotron and in inverse complex scattering. And the amount of energy lost in inverse complex scattering also depends on how early it is. So at early times, the photon density is large, so there's a lot more scattering loss. Late times, it's less. So we can do this also. So there is this system of self-similar self-coupled equations. So we can write down by solving it the number of electrons as a function of the initial pressure and final pressure, normalize it, and we can calculate what is the radio power. This is a synchrotron emission power, so it's very simple, it's like a straightaway formula probability. So what is important to understand over here is that if I have a radio galaxy with some Q and some time scale, then in principle, I can calculate the radio power at every snapshot of the radio galaxy. It's a function of time. So as the galaxy is evolving, I can calculate now, which is this power loudest. And remember, as it becomes larger and larger, the energy density becomes less and less, so radio power stops. Okay. So size larger, radio power less. And remember, because we know what is the density, I also know, and I know the energetics, so this is relativistic, I also know what is the pressure. Pressure is related to the energy. And so if I know what is the pressure of the electrons, I can calculate what is the CMB distortion. Because people who do CMB-SG, they know the CMB distortion is just an integral of the pressure around the line of sight. So now at every snapshot, I know what is the radio power. I also know what is the CMB distortion due to this radio galaxy. Both. So let's come to the first figure and try to explain what it is. As you can see over here, we have started the radio galaxy, let's say, which has some power law distribution at some different redshift, maybe at station 3, or maybe station 2 or 1. And these lines are electron population with different gammas. Gamma 2 is high energy electrons. As I told you, the high energy electrons lose energy very fast. So as you can see, very quickly it drops out of the population. Okay, the high energy electrons always drops out of the population. So only the low energy electrons live long enough to affect the dynamics of the radio galaxy. That's very important. So it also tells you that if we can measure something, we do something about it, we know about the low energy electrons well, affecting the dynamics of the galaxy over time, and we may actually try to see how low is there a lower energy cutoff. This is one of the very burning questions in radio galaxy physics. Is there a lower energy cutoff of this? As it really goes to zero, it becomes completely non-relativistic. No one knows that. People try to estimate it like by second waves. Over here, we try to do that. Over here is the radio power, function of the size. As I told you, as the size increases, the radio power drops. So you can see for three different radio galaxies at different redshifts, the radio power drops and the size increases. And this is a more correct picture. I told you the radio galaxy, after sort of burning for some billion years, stops. And then the radio power drops drastically because there is no source. So if I know, important is to connect that, I can connect my size to my radio power. That's important to see. So my equations lets me connect exactly my size to radio power if I know about the radio galaxies. I need to know about the radio galaxies, where I'm looking. I told this that if I know that basically the pressure, then the distortion or the radio semi-distortion is an integral of the pressure. So here is the distortion, the semi-distortion size of the lobe. Again, as you can see, as the size of the lobe increases, again, the pressure inside decreases. That's why they cannot go on very well, because energy decreases, pressure is connected to energy, pressure decreases, and so the semi-distortion. So again, if I look at a radio galaxy of a size at some redshift, I know exactly what is the Y distortion. Same over here, depending on the internal energies. So this makes one important conclusion from this. Both the CMB distortion, which is one messenger of the universe, and the radio power, which is another messenger of the universe, these are connected through equations for radio galaxy. So if I know if I can observe a radio galaxy in both CMB and in radio at a redshift that I measure, I can basically connect these two observations. And this unknown that goes in the theory, which is basically this central power, the time, or some other, like the slope of the electron population, the slow energy cutoff, these can be taken out. But something more interesting can be done. So we've talked about CMB, this observations of CMB distortion by radio galaxies, and I told you that the CMB distortion over here is basically non-thermal. And this non-thermal distortion actually is very, very helpful for us because it has a very, very unique spectral signature. So people who know secondary CMB or knows the Sunyaev-Zel'dovich effect, which probably some of you do, they know the important reason the Sunyaev-Zel'dovich effect has become so important in secondary CMB. This is what all this ACT Cavalier does, is because there is a unique spectral signature. It has a deficit of flux at low frequencies and an excess of flux at high frequencies. And the idea is very simple. You take a Planckian spectrum. Okay? This is the basic of everything. You take a Planckian spectrum and you upscatter some photons. This is inverse Compton scattering. So unlike Compton scattering, the photon doesn't give energy to the electron moves, it's the electron that gives energy. So upscatter the electron. So the spectrum is distorted. Now in the scattering, the number of photons are neither created nor destroyed. So the total number of photons is still. So what really happens is that some photons at a low energy goes to high energy. Which basically means at low energy there is loss of photons and high energy is excess. So the flux is low, the flux is high, and there is some crossover frequency. So if I look at the difference of flux at a source where this thing has happened or not happened, at low frequency there will be a dip, high frequency there will be an excess. That's a classic Sunyaev-Zel'dovich spectrum that is exact. And this is what people use. So if you look at different frequencies, you just need 3 frequencies. You take one frequency low, one frequency middle, one frequency high. I can basically take out this effect out of every other effect. That's the point. And over here, we can do the same. Okay. Over here, we can do the same. Let us not go into the balance over here. Because it was in PowerPoint, now I just put it into PDF. Let us look at this. So over here, what I have plotted is basically so let's look at this side. We'll just show one thing on this side, then go to the next side, and then we'll come back. If you see this red line, red dashed line, and the black dashed line on the left side, this is the frequency signature of Sunyaev-Zel'dovich. As I told you, the frequency signature shows there is less on the low frequency side, high on the high frequency side, more flux on the high frequency side, and there is no cluster. Because of this unique nature, I can pick it up. Okay. That's one thing. Different distortions of CMB has different spectral natures. So there are other distortions that are written over here. However, when I look at this non-thermal distortion, it also has a unique shape, but which is very different from all of these. And that is this green line. So because non-thermal plasma has a lot of energy, there are electrons with few energies, it can upscatter photons to really high energies, which is why it's going to very high energies. And so how high energies it will be, it will depend on what is basically the spectrum of the photons, spectrum of the electrons. So whether it's energy to the power -3 or it's -2.3 or whatever, and the lower cutoff of the electrons. So over here, what I've done is the same thing. I've just taken the absolute value. Whatever is over here, I've taken the absolute value over here. Okay. And over here, I can see, depending on whatever is the lowest cutoff of the electron energy, P gives you an idea of the lowest cutoff. So your gamma and P is like this. I have different spectral features, and it moves. The midpoint is crossing over, moves to the right. Also, the slope is different. All these things are done with a slope of minus. All these things done with a slope of -3. Except the magenta is done with a slope of -2.3. Again, as you can see, your amplitude and your frequency dependence. Now, why does it become important? It becomes important because you can come back to the left side picture, and these dashed vertical lines are the frequencies of Lyman's array, which is the next after act. Okay, so these are the frequencies in sinusoidal motion. So as you can see, the sinusoidal measures in enough number of frequencies that I can distinguish between these different frequencies. So already in Simon's array, I can take this out at many signals. This non-thermal distortion, if it is there, can be taken out at tens of signals. And there are proposals where there will be hundreds of frequency bands. So this is what the brave new world is. It will have observations where the frequency coverage will be in many frequency bands up to 1 terahertz. And that way, one can take out all these different effects. Not only that, once we have frequency coverage, we know just from the frequency spectrum over here, what is the slope of the energy electrons of an energy, so what is the power slope, and what is the minimum energy it goes. So now, once we go into this brave new world of secondary CMB, along with the old world of radio galaxy observations in radio, we have everything that was unknown to us. We know what is the Q, we know what is the T, we know what is the P, the gamma, everything is known. Nothing is unknown. Okay. But this is with single objects. In general, the universe is full of radio galaxies. So what I was saying till now is that if you look at one radio galaxy, so you see it in radio observation tells you, oh, there is a radio galaxy over here. You can see. You go and look at it in CMB, measure it, and you can do all these things. But suppose you don't know anything about radios, just look at the CMB map, initial map that I showed. Okay, this will have observations, imprints from all the radio galaxies all over, and there will be fluctuations in the CMB sky from all the radio galaxies. So there's full of radio galaxies, and you can basically look at the fluctuations. Now, why are we excited about it? So people had tried to look at radio non-thermal CMB SZ for, I don't know, 40 years, 50 years now. In fact, when I did my PhD, I proposed in one of my chapters in PhD that you can do this, and it went to the referee, and referee is actually one of the most well-known name in SZ observations, Walkinshaw, and his thing is that this can never happen. That was in 2001. 2016, we have the first observation of secondary CMB from radio galaxies. So yes, it has happened. Okay. Your sensitivity has got better, your angular resolution has got better. So there is a map of the sky. You have the bullet clusters over here, outskirts of the bullet cluster. Go back and zoom. This is SZ signature of radio galaxy. So the radio galaxy center is over here, and this is the radio lobe. So we have actually an observation of radio galaxies. It can be done. First, only observations, but done. Now, what we do if you can do this? Remember, I told you that given the size of the radio galaxy, if I know this redshift, then the size tells you uniquely what should be its SZ, what should be its CMB distortion, and what should be the radio flux. So if I map my radio flux versus CMB distortion, and the observation tells you that you're over here, or here, or here, whatever, this can only happen for a unique radio galaxy. Okay. It cannot happen for different radio galaxies. So what that paper by Malu et al. Told us that for a radio galaxy, radio cocoon, for which your radio power was already known to be in this band, they found a CMB distortion, which is around here, And this comes if we have a unique physics, unique radio galaxy. Okay. And so I can tell you exactly what is the size of the radio galaxy, or what is the central engine capacity, whatever, for the galaxy. So this is already known. This was not known. So remember, previously people was only doing this. So with this, none of the models can be broken. As soon as you have a Z, as soon as you have CMB, and as soon as you know what is the power law index, what is the minimum energy, sort of immediately can break the distances. And this gives us the first limit ever on the lowest energy cutoff. So people have wanted to know whether the radio electrons go to really non-relativistic or still relativistic. We now know it is slightly more than relativistic.
So the length scale for this, so it should be able to help in understanding of the dark matter. Is the galaxy scale, right?
So dark matter
Cluster scale.
Dark matter doesn't come over here.
Can one relate it?
There's no
Not
dark matter over here. But what one can do is something.
For the spectrum,
No, dark matter. This dark matter is dark matter here. CMB distortion it doesn't depend on the nature of dark matter. There is something that we can do immediately, which is one observation. So it's something that we have tried to do for like 60 years. Okay, now this is a very, very complicated part, but I want to really take 2 minutes to explain to you this. Why these radio galaxies will become very important in the future. So over here, this very, very busy plot on the bottom is frequency, and on the y-axis is the intensity of distortion from different things that can give distortion. So there is, when people look at CMB, they have to remove whatever the contaminations, dust, synchrotron, they all have some frequency spectrum, which is very, very different. That's why they can take these things. And they will do these things and keep on removing dust and infrared background and synchrotron and X-ray and this and that, on doing it. And the goal of doing it, because they want to do this holy grail of physics, which is this early universe mu-distortion. And that lies over here. This pink curve at the bottom. This pink curve at the bottom is what we're looking at. Holy grail. That's what they want to do. They want to remove all of these. And they can do this because they have very different, although it is so much less in power, it has completely different frequency spectrum. And so if you have enough frequencies, they can do that, and then they can cut a universe. Spoil sport is radio galaxies. Because there's radio galaxies, now we have this magenta one. So now as we see, you cannot, radio galaxies are ubiquitous in this universe. You cannot say that there's no radio galaxies. The radio galaxies, the radio couples, they are going to distort. So now if you are going to find this magenta line, you will going to find this line. This pink line. You're going to find a pink line, you're going to find something. And if you want to do this, you better understand. Otherwise, you cannot do this. So, CMB distortions in this brave new world of secondary CMBs will be very important to understand. All these new distortions, because unless you can remove all these new distortions, you cannot. That's a very, very important part of it. Let's move over. If you can get it, there'll be lots of interesting science. I'm not going to go into this. One of the very interesting things that you can do, and I've not done, I've not connected it, is that one can get this connection between the central black hole mass and the mass of the halo, which is known as Gregorian relation. Black hole mass to halo mass connection, unprecedented precision. If you can do this kind of things. But let me in the next, so I think I have like 5 more minutes. Let me do one last interesting thing, which I think should be very, very useful. So it's a crazy idea. It's a crazy idea, but sometimes crazy ideas don't really do this. So let me. So people may have known, I don't know how many of you know, that there is a way of measuring the Hubble constant with using CMB distortions and X-ray of galaxy clusters. It's a classic measurement of Hubble constant. And it's very powerful because it is distance scale independent. For example, when I look at supernovas, all this problem with supernova Hubble constant measurement is that it depends on how you calibrate. So to calibrate locally, then use that to calibrate next, then use that to calibrate next. But this classic thing, which was proposed by Silk and White in the 1970s, mid-1970s, is the only one distant ladder independent measurement. So we look at galaxy cluster, to measure the extra flux of the galaxy cluster, and to measure the CMB distortion of the galaxy cluster. The idea is very simple. Your CMB distortion of the galaxy cluster depends on basically the number density times the temperature of the gas times the length. And X-ray becomes the number density square root temperature half. I can cancel the density from this two and get an idea of the size, physical size of the galaxy cluster by looking at CMB distortion and looking at the X. So if I know the CMB distortion from a galaxy cluster, I know the X-ray flux of a galaxy cluster, I can estimate this should be the size of the galaxy cluster. Now, when I know this is the physical size, this size exactly in megaparsecs, the size of the galaxy cluster. Now I'm looking at this galaxy cluster in the sky. So I know how much it occupies its position in the sky. So I've got to know what's the angular size of the galaxy cluster. I've estimated the physical size. I can see the angular size. I take the ratio of it. That gives an angular diameter distance. And then cosmology. An angular diameter distance depends on the Hubble constant. So if I can estimate this and observe the galaxy cluster because I have to observe it, I know what is the Hubble constant. And this is what has been used to Hubble constant, and this is what is all the different observations of Hubble constant done in the years. Many. And also after Planck. These are systematics, but it's very. And this is, as I said, 40 years has been the only distance ladder independent galaxy. Now, can we do the same thing with radio galaxy cocoons? Just like we were over there in galaxy clusters, we were doing X-ray and CMB distortion. Over here, we are doing radio observations. So your radio flux, forget about, you can write the exactly radio flux, but approximately your radio flux is basically square of the density of the electrons multiplied by the length or the size of the cocoon tubed. That's your radio flux. That's the back of the envelope calculation. And you can do it up to in detail if you want. The same electrons which gives the radio gives you your SZ distortion. The SZ is the density times the length. Remember, SZ is the pressure along the line of sight, or relativistic the pressure system. Okay? So if I know this two, these are the two observations. This is the observation, this is the observation. I can combine them. I can have an estimate of the length scale, size of the cocoon, estimate of the size of the cocoon, just like we had an estimate of the size of the galaxy cluster. Now I have an estimate of the size of the cocoon depending on the radio observation. So look at the cocoon in radio. Till now, people are only looking at radio, they couldn't do it. Now I can look at it in SZ also. So now I can estimate the size of the cocoon. And I can see the cocoon. So again, just like galaxy cluster, I have the physical size, I have estimated it. I have the angular size. And I can, take the ratio, and that will depend on the Hubble constant. So let us do it with the one observations that we have got. One place where we'll have observed the radio galaxy. And we get something interesting. So just like the previous plot, I have the radio flux over here and CMB distortion over here. And for that one cocoon, there is one observation. So one observation says that you have a CMB distortion, something over here, something here, and gives you some region of space over here. So whatever be your model, it should give a size that should give you this region of space. Because remember, the size, the radio flux was dependent on the size, the semi-distortion is dependent on the size. So you can look at the observed region, X and Y, and look at the size. And it turns out, if I do it for this object, the size is approximately 1 megaparsec. The error bar depends on the band of the radio observation. So 1 megaparsec is the size. That's the estimated size of the radio observation. And we are looking in the sky. So we know from the picture that I showed you, I can go over there and really look at the size, the angular size over there, because the picture is over here. So I know what is the observed size. And so this estimated size by the observed size is your Hubble distance to here. That gives me the Hubble constant. So I have a new way of measuring Hubble constant. Right? These were all the things that people measured on the right directions from X-ray and different clusters. But one radio galaxy I have one, which is very much in the ballpark. Completely new, completely novel way of measuring. Look at all the Hubble constants measured. These are all not from one sources. Most are from many average of many sources. Only this one is from gravitational wave one source. One number from one radio galaxy is not bad. So we have opened up a completely new way of measuring Hubble constant. Remember, there are hundreds of thousands of radio galaxies. Just need to follow every radio galaxy that has a cocoon and has measured radio fluxes, and there are many already fetched and built. There are many. So we are really at this juncture where a brave new world can be said. We are talking about new secondary semi-distortions, completely new nature, and gives us a completely new angle at how we can get it. So I will not talk about, there are other things that we can do with secondary series and I'll talk about it. I'll come quickly to the conclusion. Thank you. Thank you, slide. So here's a new line that I showed you. One should not only think of this line in terms of just another line, you should think of things completely as something which is completely different physics. People have been working on thermal distortions for 30, 40 years. This is the first thing which is a non-thermal distortion. If you can get this, you can find out, for example, we can know what is the physics of the radio galaxy, we can constrain it, cosmology, we can constrain, black hole to halo mass, these relations, know how it is. And a very unique way of so that's where this brave new world comes. So I'll say welcome to the brave new world of new secondaries. So I'll stop over here. Thank you. Okay, questions? Curious, how many over here are from cosmology, like the cosmology, like this? Okay, because I was wondering, is it everything completely new? Because
Yeah, the top was great.
Very accessible.
Question? If you don't have a question, then I tell in my class.
no, but
Audio might not have
what is important is that you can always ask later.
Okay, I have a lot of questions. So all of the different majors in your class, do you have to correlate them, right, to get an exact physics of radio
When you
galaxy?
say correlate them, what do you correlate what?
All of the different frequencies that you said that it has different nature.
So,
Do you
for
need
example,
to-
let us say I'm taking, let's say, any distortion which has a frequency dependence. You basically look at the sky at different frequencies. So if that blackboard over there, the picture had a frequency dependence, but I'll look at this picture at this frequency, this frequency, this frequency, this frequency. And then every frequency observation will have at that frequency will have some number with some error bar. And I know what's the frequency dependence. I will see if I can match with the observation.
Yeah, that is a matching part, but I'm saying that whether to get an exact nature of a distant galaxy is that. Because if it can emit in different frequencies.
Yes, so let's exactly. So if you remember this, every so when you get a when you observe something, the photons that are coming to us, you cannot differentiate whether this photon is coming from, let's say I have 1,000,000 photons coming to us. Okay. This 1,000,000 photons are made up of photons that is coming, let's say this object, yeah, due to synchrotron emission from the galaxy, due to free emission from the galaxy. Now, 1,000,000 photons at this frequency, 1,000,000 photons at this frequency, 1,000,000 photons at another frequency. Each of these emission has a spectral form. So, which basically means I can do a best fit linear fitting whole thing.
Yeah,
That's what you do.
so you do with this.
Yes, of course. Otherwise, how do you do?
Some other question? Okay, so any question from online?
No, there is no questions online.
Thank you. So let's thank the speaker again.